In this video, we're going to look at what's called impulse. Right? Impulse is defined as the product of net force acting on an object and the time the net force acts on that particular object. The product, which means you're going to multiply the net force acting on an object and the time which the net force acts on that particular object. So impulse, this is the mathematical relationship. Impulse is equal to F net times delta t. So F net times delta t is impulse. Okay. We must also know that impulse is a vector quantity, which means it has direction as well as magnitude. The SI unit of impulse is Newton second. So we say Newton second. That's the unit for impulse. Now, we looked at Newton's second law in terms of momentum. We saw that F net is equal to delta P over delta T. Now, if you multiply both sides by delta T, we're going to have F net times delta T equals to delta P. All right. So this expression here on the left is what we call impulse. The product of net force and time is what we call impulse. So we can express this particular equation in many different ways. We know that our F net times delta T from this equation is equal to delta P. So we can say F net times delta T, which is the impulse, is actually equal to delta P. We can also express this in a different way. We can say F net times delta T equals to the mass multiplied by the final velocity minus the initial velocity of an object. This is how we calculate our delta P. So we can safely say impulse of an object is actually equal to delta P, or the change in momentum. So the impulse is equal to the change in momentum of an object. So these are all different expressions to express the same thing. But impulse is defined as the product of net force and time. Okay. So let's have some calculations. Let's have an example here. So in this question here, we're told dancers have to learn many skills, including how to land correctly. A dancer of mass 50 kgs leaps into the air and lands feet first on the ground. She lands on the ground with a velocity of 5 meters per second. The velocity landing on the ground. As she lands, she bends her knees and comes to a complete stop in 0.2 seconds. So this tells us that the final velocity here is actually equal to 0 meters per second. Her initial velocity is this one here as she lands on the ground. Now, for her to come to a complete stop, in other words, for the velocity to change from 5 meters per second to 0, it took 0.2 seconds. So this is our change in time. And then, of course, we have the mass. Now, the question says, calculate the momentum with which the dancer reaches the ground. In other words, we want the initial momentum before she actually collides with the ground. So we're simply going to say, okay, let's just take down as positive, right? And then we're simply calculating momentum here. So P is equal to mv. The mass is 50 kgs. The velocity is 5. 50 times 5 will get 250. That's kgs, meters per second, downwards. So that's the momentum of the girl as she lands on the ground. The second question is saying define impulse. So we know impulse is the product of net force and the time for which the net force acts on the object. Right. 1.3. Next, I want to calculate the magnitude of the net force. Calculate the magnitude of the net force acting on the dancer. So it's just the magnitude here. We won't need to state the direction. However, we need the direction for our calculations here. So we are still taking down as positive. All right. Then how do we find the net force? So we have our net force, we have our change in time rather, and initial and final velocity. So we can use the impulse equation here. So we simply say the net force times the delta t equals to the change in momentum, delta p. So F net multiplied by 0.2, which is our delta t, is equal to the mass multiplied by the final velocity minus the initial velocity. So F net times 0.2 is equal to 50 multiplied by the final velocity is 0, the initial velocity is 5. Alright, so I have F net times 0.2. This gives me negative 250. So if I divide both sides by 0.2, so I'll say over 0.2 this side, over 0.2 on the other side, then I cancel this. My F net becomes negative 250 divided by 0.2. I get negative 1250 newtons. So therefore, my net force is equal to 1250 newtons. So no need to state downwards or upwards here because the question just wants the magnitude. Right. So that's the force that is needed for her to change her momentum, or rather to change her speed from 5 meters per second to 0 meters per second in 0.2 seconds. In the second question here, we're told that Percy, with a mass of 75 kgs, rides at 20 meters per second on a quad bike motorcycle with 4 wheels with a mass of 100 kgs. So we have the mass of the rider and we have the mass of the bike, which is 100 kgs. He suddenly applies brakes when he approaches a red traffic light on a wet and slippery road. The wheels of the quad bike lock. The bike slides forward in a straight line. The force of friction causes the bike to stop in 8 seconds. So he's coming to a stop in 8 seconds. Right? Very important. Highlight your given information here. So we have the mass of the rider as well as the mass of the bike here. So it means that our combined mass is actually equal to 175 kgs. Right? He is riding at 20 meters per second. So this is our initial velocity with which is traveling. He comes to a stop, so it means our final velocity here is 0 meters per second, and we have our delta t, which is 8 seconds. Now, define the concept of momentum in words. So we know what momentum is. It is the product of mass and velocity of an object, right? So we're not going to worry about that. 2.2, calculate the change in momentum of Percy and the bike from the moment the brakes lock until the bike comes to a stop. Right, so we're just going to state our direction here. So I need you guys to always practice writing this statement down. So we're just taking the forward direction. Take the forward direction as positive. We're not told whether it's going to the right or to the left, to the east or to the west. So you just say wherever he was going, that particular direction is positive. So we want to calculate the change in momentum. Calculate the change in momentum of Percy and the bike. Right? So we say delta P equals to the mass times the final velocity minus the initial velocity. The mass here is 175 kgs multiplied by 0 is the final velocity, 20 is the initial velocity. Okay, so take out your calculators, multiply 175 multiplied by 0 minus 20. We get negative 3,500. So that's kgs meters per second, which is actually equal to 3,500 kgs meters per second in the opposite direction. Okay, opposite direction. So you can see that we're getting a negative answer. So it means that it was actually, the momentum actually changed in the opposite direction so that it comes to a stop. 2.3, now we want to calculate the average force, right? Determine the average force, average frictional force. So this means that we need to calculate the net force, because the force that is causing him, or rather the force that will cause him to come to a stop, is actually the net force, right? Remember, we say that for the momentum of an object to change, we need a net force. So in this particular case, he is just sliding on a road and frictional force is acting on him. It means that that particular force is actually the net force that causes his momentum to change. So the question is asking for the net force acting on him, right? So we're still using our, right, we're still taking, right, take the forward direction as positive, direction is positive, fine, right? Okay, so we say what? The net force, F net, times the delta T equals to delta P. So the net force, F net, multiplied by the time that the net force changes, it was 8 seconds, equals to our delta P. Remember, this impulse is a vector quantity, so we have to take direction into account. So we're using this negative 3,500, right? And then from here I divide both sides by 8. It means that my net force is actually equal to negative 3,500 over 8. That will give us, let's see, so I simply divide this by 8. I get 437.5. newtons. This is a force, right? Therefore, the F net is actually equal to 437.5 newtons in the opposite direction. In the opposite direction. Since my answer here is negative. And it makes sense because we know that frictional force is a force that opposes the motion of an object. So we expect to have a force opposing his motion, and that opposition to the motion causes his momentum to actually decrease all the way to 0. So that is how we use momentum to determine the force and the change in momentum that is acting on an object. Right?